Hello folks, today I am ready with the topic here. The topic says cross fields and their use in determining E by ME, that the specific charge of an electron. So E is its charge and ME is its mass. So E by ME of an electron by Thompson method. So this is the topic the topic that we are going to study was somewhat used by Mr. Thompson to determine this thing. So first of all, let us discuss about cross fields. So cross fields means that it is the field, combined field made of electric and magnetic field. They cross each other. They cross each other and they produce deflection of any charged particle in opposite directions. They cross each other. First requirement is they have to cross each other and they produce deflection of charged particles in opposite directions. For example, let me say like this. So if I have got a certain electric field like this, this is positive and this thing is negative. This is the electric field. So in this region we have got electric field. Now what I do is let me produce magnetic field also in the same region. So let me apply magnetic field in this region, somewhat like this. Somewhat like this. So it will be crosses here, all crosses. Cross means that the magnetic field is going from us to the board. So it is going towards the board. It is entering the board, let us say. Now if a positive charge particle enters here from the left, if any positive particle enters here from the left, what happens is the electric field will try to deflect it downward. It's because this positive is repelled by this and attracted by this negative. So that's why it is carried downward by the electric field. On the other hand, what happens is the magnetic field also creates some sort of force here, which is called as Lorentz force. So the direction of Lorentz force is given by the left hand rule. So what happens is this is the magnetic field. It is pointing to this direction, going away from the camera, from us, let us say, and the charged particles are going here, positive charged particles. The force is here. So that means these charged particles will be deflected upward by the magnetic field. Now since I have denoted red color to show the magnetic field, I am doing this path also in red. So the magnetic field will try to send these particles upward. So this type of field is what we call as cross fields. So in a cross field, if I send particle from the left, positive particle, they will be deflected in opposite directions. So they cross. So that means one is like this, and one is like this. So they cross each other. See the angle. They cross each other. One is like this, one is like this. They cross each other like this. So that's why they are known as crossed fields. Now Mr. Thompson used this method to determine E by ME, specific charge. Now here, this is positive charged particle. So that's why the deflection is like this. Now if had it been a negative charged particle, so what could have happened? So what would have happened was this thing would have reversed. These things would have definitely reversed. So let us work them out. Let's work them out. So let me redraw these spoiled figures like this. So the electric field will now deflect this negative particle upward, because here we have negative, positive, this is also negative. So it will deflect upward somewhat like this. It will deflect upward somewhat like this, done by this electric field. And these magnetic field, what they do is they will exert an opposite force compared to this. Initially it was like this. Now they will exert force like this. So that's why the magnetic field will cause these particles to go there. So again they are acting opposite. So Mr. Thompson did this thing for electrons. So he used electrons and found a value for this E by M. So these are the cross fields. Now Mr. Thompson did somewhat like this. He had a source of negative particles, which we call as cathode ray gun. So it is like a tube light, slightly modified form of tube light, or we can say modified form of the cathode ray monitor, the picture tube of the cathode ray monitors, which was prevalent till 20 years ago. So now like this, and he used a certain screen for the particles to land. So it's a screen here, it is a screen here, SCREEN. So this is the midpoint. So this will the distance here will record the deflections. So this deflection is due to electric field, and this lower deflection is due to magnetic field. So this is due to magnetic field. So Thompson did such arrangements. Now what happened was, he could switch on the magnetic field, he could switch on the electric field, or he could switch on both according to his wish. So what he did was, initially he switched on both electric and magnetic fields, in such a way that this thing goes undeflected. This thing went undeflected. So at that time what should have happened was, the force, electric force, should have been equal to the force magnetic. Otherwise they could not have gone straight. So the electric force is equal to E into E. E is the electric field strength, V by D. This is equal to B E V. It's because this Fm is equal to B Q V sine theta. And here E stands for Q, the charge, and the sine theta is equal to 90 degrees. It's because the particles are going like this and this is going like this. So this and this will definitely form angle 90 degree, which I have to look somewhere like this. I have to look like this. So let me pick up the marker. So yes, I did. So now, so when they're equal, I must do like this. So I can just cancel this E and E, which gives me velocity equal to E by B. So this is a revolutionary equation of those days, because he did not need any other method to find the velocity of the electrons. No other method. Simply you make them balance, the force balance. You make the electrons go undeflected. So at that time the value of B and the value of E is V by D. So the ratio of E and B gives the value of velocity. So that was easy. Then what he did was, he switched off the electric circuit. So only if he did so, the charged particles will go like this. So at that time the Lorentz force Fm is responsible to move it in a circular path. So that is equal to Fc, centripetal force, which gives us, or BeV is equal to mv square by r. So here I can cancel V and V. What I am doing is, I am trying to find E by m. So let me write here E here to denote it, to denote that it is the mass of electron. So this gives us E by me is equal to V by B and then r. And this V is E by B here, so it's equal to E by B, then again B r. So that's equal to E divided B square r. The value of B can be determined by flux meters and several other devices. E can be known by the equation V by D, and r can be geometrically determined by drawing a normal here, and by knowing the radius, by knowing this angle. So this r can be known, and that gives the value of E by me. In those days its value came to be 1.8 into 10 to the power 11 coulomb per kg in those days. Nowadays the accepted value is 1.76 into 10 to the power 11 coulomb per kg. So pretty accurate and precise value in those days. Now this method not only determined the value for E by m, but also it gave us a new technique of velocity selection of charged particles. It means that selecting charged particles according to their velocities. So we just want to segregate them according to velocities. That means we want charged particles of a particular velocity only at a particular place. If so, we can apply this method. So what we can do here is, for example, this was in a balanced condition. In the balanced condition, we have got Fe equal to Fm, and this EE is equal to BeV. This equal to this equal to this. Now, if in these among these electrons there are some high velocity electrons, there are some high velocity electrons. So if so, then this Fm will be more. If Fm will be more, those high velocity electrons will be coming to this side. This side. So that means those electrons which come to this side are high velocity electrons. Similarly, we have got low velocity electrons. So in that case, this force will be less and this will be greater. So those electrons will be going upward. So that means whoever are going upward will have that will mean that they have got low velocity. So what I can do is now, if now they are separated, what I can do is which I do want. So I have to decide. If I want high velocity electrons, then what I should do is I have to place a slit. Let us remove this screen. So this is a high velocity region, high velocity region. This is a low velocity region. So if I want high velocity electrons, I can place a screen here, I can place a slit here and make them enter from here. If I want a low velocity electrons of certain velocity, so I can place a slit here and this should be blocked. So that's how we can obtain the electrons according to their velocities. So this process is called as velocity selection of charged particles. So Thompson's method, this method of using cross fields to determine E by M, also gave us another method to select charged particles and send them somewhere according to their velocities. According to their velocities, like this.